For number 16, it is found that the gas loading in the 91.4 centimeters by 121.9 centimeters breaching of a pulverized coal-fired plant is 9.61 grams per cubic meter and the gas velocity is 12.2 meter per second. A collector of 80% efficiency is installed. How much dust can it be expected to collect? So, per kilogram per hour. So for number 16, so we have a gas loading of 9.61 grams per cubic meter. So total flow of solids is equal to gas velocity multiplied to breaching area times gas loading. So our required here is the dust collected. So first we have to solve for this. So substituting the values. So from this formula, so equal to 12.2 meter per second times 9.14 centimeters times 121.9 centimeters divided by 10 raised to 4 centimeters squared over meter squared times 3,600 seconds per hour times 9.61 grams per cubic meter divided by 1,000 grams per kilogram, which is equal to 470.3 kilograms per hour. So, to solve for dust collected, so it is equal to 0.8, which is 80% given in the problem, times our 470.3 kilograms per hour, so which will result to 376.24 kilograms per hour. Problem number 17. A spreader stoker plant is assumed to have a gas dust content as shown in figure 12-24B and a gas loading of 4.58 grams per cubic meter. If a lever type collector is installed, which characteristics as shown in figure 12-25, what gas loading can be expected at the collector's outlet? So for number 17, so for spreader stroker figure 12-23B use 50 microns. So for lever type collector figure 12-25% collected is equals to 80% or 0.8. So letting X is equal to our gas loading. So at the collector's outlet. So substituting the given from the problem. So 4.58 minus X divided by 4.58 is equal to 0.8, which is the percent collected. So deriving this equation, X now is equal to 0.916 grams per cubic meter. Problem number 18. An air preheater consists of 6.3 mm flat plates 91.4 centimeters wide by 8 meters high plates spaced 31.8 mm OC. Both edge passages are for air mass flow on 20,860 kg gas per meter squared hour. Flows gas 45,359 kg per hour, air 38,555 kg per hour, gas in at 371.1 degrees Celsius, out at T sub-zero, air in at 15.6 degrees Celsius, out at 148.9 degrees Celsius. A. Find the T sub O if C sub P is 0.24 for air and 0.26 for gas. B. Find the necessary heating surface using equation 12-1. So let's proceed to 18. So for letter A, for the so from the formula, W sub G is equal C sub PG times delta T, T prime sub I minus T prime sub O is equal to W sub O times C sub PO times T sub O minus T sub 1. So from the problem, our W sub G is equal to 45,359. Our CPG is 0.26. So our T prime sub I is equals to 3,711 minus our T sub O, which is our required. So is equal to our W sub O, which is 38,555 times our CPO, which is 0.24 times our delta. I mean our the difference within these two, which is on 148.9 minus 15.6. So deriving this, which will give us the T prime sub O is equal to 2.66.5 degrees Celsius. Problem number 19. The air preheater described by the previous problem has 371.6 meter squared heating surface in the plates. How many plates are required? What is the necessary height of each? So for problem number 19, we're going to find the number of plates and of course the height. But first, we have to solve for the flow area of the gas, which is equal to 45,359 divided by 26,860 will give us a 1.6887 square meters. So for rectangular space area, we will going to divide this from 0.194, which is equal to 1.8476. So for number of plates, so 2 times 1.8476 divided by 0.0318 minus 0.0063 plus 1, which is equal to 146. And for the height, 371.6 divided by 146 times 0.914, which is equal to 2.78 meters. Problem number 24. What pressure centimeter of water will give air at 93.3 degrees Celsius and 10.2 centimeter static pressure a velocity increase from 0 to 731.5 meters per minute? So for number 24, so our V sub 2 is equal to 731.5 meters per minute, which is also equal to 12.19 meters per second. So as V sub 1 is 0 and C is assumed 1, so therefore H is equal to V sub 2 squared divided by 2G. So our V sub 2, which is 12.19 meter per second, we just have to square it divided by our 2G. Our G is 9.81. So therefore, our H is equal to 7.57 meters of air. So 93.3 degrees, so we have to convert it into Kelvin, so which is 366.3 Kelvin. So static pressure of air is equal to 1.034 plus 10.2 times 1 divided by 1000, which is 1.044 kilogram per centimeter squared. So for the density of air, 1.044 times 10 raised to 4 divided by 29.3 times 366.3, which is equal to 0.9727 kilograms per cubic meter. So 10 y sub w is equal to 757 times 0.9727. So deriving this formula, y sub w now is equal to 7.57 times 0.9727 divided by 10, so y sub w is equal to 0.736 centimeters of water. Problem number 25. Find the draft loss in rectangular breaching 2.59 meters by 3.66 meters by 30.48 meters long when 196 cubic meter per second flue gas of 0.769 kilogram per cubic meter density are flowing. So next would be our problem 25. So D is equal to lowercase d over 10 times F B squared H divided by 2 GR centimeters of water. I add 57% for the rectangular duct. So H is equal to 30.48 meters. So solving for R is equal to A divided by P, which is 2.59 times 3.66 divided by 2 times 2.59 plus 3.66, which will give us a result of 0.758 meters. So next is our V. V is equal to Q over A. So 196 divided by 2.59 times 3.66, so which will give us a result of 20.68 meters per second. For flue gas F, is equal to 0.0114. So our D is 0.769 kilogram per cubic meter. So our D is equal, our uppercase D is equal to substituting these values from to this formula, which will give us 0.769 divided by 10 times 0.0114 times 20.68 squared times 30.48 divided by 2 times 9.81 and 0.758 times 1.15, which will give us a result of 1.085 centimeters of water. Problem number 26. What is the friction loss centimeter of water in a 2.44 meter diameter chimney 61 meter high up which gas is flowing at 9.14 meter per second? Gas density is 0.6776 kilogram per cubic meter. Next is number 26. So it's kind of similar to the number 25. So uppercase D is equal to D divided by 10 times F V squared H divided by 2GR, which is the centimeters of water. So H is equal to 61 centimeters. Our R is equals to D divided by 4, which is 2.44 divided by 4 is 0.61 meters. Our V is 9.14 meters per second. Flue gas F is equal to 0.0114 and our D is 0.6776 kilogram per cubic meter. So substituting all these values to this formula, so it is now equal to 0.404 centimeters of water.